In class, I mentioned that it will be important for you to review, say, the definition of a random variable and some basic properties. And so in this video, I want to remind you of the definition of expectation, the expected value of a random variable, and also the definition of variance. And then we'll also look at properties of expectation and variance. And really these things will be pretty essential to calculations and proofs that we do throughout the rest of the semester. So really having a good conceptual understanding of expectation and variance will be important. So as we often do at this level, we will define expectations separately for the discrete random variable case and then the continuous random variable case. And just note that at a certain level of generality, which requires some measure theory, we could have definitions that combine the two, but for our purposes it will be enough to separate them out. So for expectation of a discrete random variable, we'll use the notation e of x, where x is our discrete random variable, and the expectation will be a sum, and I'll say a sum over x. So what I mean here by x will require a bit of explanation, and really what I mean is that we're going to sum over all of the values for which there's a non-zero probability. So take a concrete example like the binomial random variable. The binomial can take on 0, 1, 2, up through some natural number n. And in that case, when we calculate expectation, we'll sum over those values, right? 0, 1 through n. And so that's what I mean by that shorthand x. And so what we sum over are each of those values that the random variable can take on times the corresponding probability that the random variable is equal to that particular instantiation. So you could think about this as like a weighted average, right? The probability mass function, p of big X equal to little x, provides the weight, and then you multiply that by the actual value that the random variable could take on. So the continuous case is similar, same notation, so we have e of x. And of course, in the continuous case, the sum won't make sense, and we will integrate. And we will integrate over a region. Now, we could write this in different ways. Maybe I'll write it like this. So we'll really integrate over the whole real line, and we'll integrate x times now not the mass function, but the probability density function. And we'll integrate over x. But of course, if the support of the distribution, meaning all of the values of x where the PDF is not 0, if that support is something that's not the real line, then this integral will be 0 in those places because the PDF will be 0 in those places. So for example, if you had an exponential random variable, the support is all positive real numbers. And so integrating from negative infinity up to 0 won't make any difference because the PDF will be 0 there, and that means you'll get a 0 as part of your integral, and then the real important stuff will come when you integrate from 0 up to infinity. The PDF won't be 0 there, and so you'll have a non-trivial result. Okay, so that's expectation for variance. I'll write the variance definition in terms of expectation, and so it will work for either continuous or discrete. It's just that you plug in the correct type of expectation. So the variance of a random variable x is equal to the expectation of the square of x minus the expectation of x. So the variance is supposed to tell us something about how spread out our values are, right? How much variability is in the random variable. And expectation is supposed to tell us something about like the center. It's a measure of center. All right, in the next video, we'll take a look at some important properties of expectation and variance that will be important for the course.